bit too much. Can you see the screen okay now with the lights as they are? I'll try to... Is that a bit better? Or? Yeah. Then we'll try that. So, we were talking about hydrodynamic dampening, and we got to the causes for the hydrodynamic dampening. So we talked about the pressure buildup in front of the object, and then we also get a pressure reduction behind the object, and we also get vortex creations because of these turbulent flows. And those are especially created along sharp edges. Vortexes can be created along more sleeker edges and stuff like that, but especially with sharp edges, you will definitely get turbulent flows across those sharp edges. So the vortex creation, of course, creates this turbulence, and the turbulence also creates a disturbance in the water, which adds to the drag in this case. It can be especially negative with these vortex creations if you are moving something back and forth in the water, because then you will constantly be moving it into an area where you've just created a lot of vortexes. So that if you're either moving an ROV back and forth, then it's going to be moving into turbulent waters all the time. Or if you have an object that is basically just hanging from your crane, but your ship is experiencing heave because of waves. So then the object will, of course, be lifted and lowered as the ship is lifted and lowered by the waves. And that it means that every time it's lifted, it will create vortexes underneath it. And then when it's lowered back down, it will be moving through those vortexes, creating more vortexes on top of it and getting more resistance due to the vortexes. And I just want to repeat what I said once in one of the early lectures with regards to turbulent flows and everything. It's not something that we can calculate. We don't know exactly about turbulent flows. So that it's you will get a Nobel Prize in physics if you figure it out, basically. It's on that stage. It's one of the things that we just haven't been able to figure out completely, so that we basically can't sort of do calculations to tell us exactly how the turbulent flow is going to behave. If we had been able to do that, we would be able to do quite a lot of improvements on any gear that uses flow rates. So any piping valves in hydraulics, anything that utilizes flow would have great improvements if we knew how to calculate this. We know how to calculate it as long as it's a laminar flow. That's not a problem. Then we can calculate it pretty accurately also, so that's not a problem. But as soon as it turns turbulent, we have troubles. We can do approximations based on lab results and experiments and stuff like that, but we can't do exact calculations. And we usually assume that the hydrodynamic drag is proportional to the square of the flow velocity. So basically, not the velocity of the object itself necessarily, but the velocity of the water particles that are streaming past it. So for an example, if you are holding your object still, motionless, basically, you are just hanging it from your ship, and you suddenly have a very powerful ocean current moving across the object, then there will be quite a lot of flow velocity past it, but the object itself won't be moving. So it's important to realize that it's the flow of the water and not the flow of the object necessarily. Usually, we determine the flow of the water by putting it relative to the velocity of the object. And if the water is fairly calm, fairly still, the flow of water will be more or less the same as the velocity of the object. So then we are okay when doing calculations. But as soon as you start putting in heave motions with waves and everything, then you suddenly start to get a very complex picture of how this works. The good thing about that is that like DNV, they have recommended practices of how to do calculations on marine operations. I think it's, if I remember this, we used this one in my bachelor thesis, but it's DNV RP for recommended practice, and then it was H103, I think it is, which is the recommended practice for marine operations, so basically lifting and lowering stuff out at sea. And in there, if you start going through each of the chapters in that recommended practice, they are going to tell you how to assume this and assume that, and how to calculate the flow of the waves relative to the movement of your object and everything like that. So, and it's pretty straightforward if you just sit down and go through each of the chapters with them. So basically, what these recommended practices are, they are basically textbooks on how to do stuff. So it's a very nice thing to look at. If you have any intentions of working towards offshore, maybe even being an offshore engineer where you're actually on a vessel participating in lifting operations and the planning of those and everything, I would highly recommend that you start looking at it in your spare time with this one, because that's going to be your Bible basically when you're out working. And it's available for free from the DNV site, so it's not a big problem getting hold of it. You get a downloadable PDF of it, so it's a nice thing to have. I think it's 120, 150 pages or something like that. And all the way at the end of it, we have a lot of the simplified methods of calculating added mass and drag and everything. So it's a good way of looking at it. And they're basically the same as we're going to look at here when we're coming. They might have a bit different way of defining stuff than what's being done here, but it's the physics is the same anyway. So, and here we also put in a coefficient when we're calculating, a drag coefficient, just as we had an added mass coefficient, just to get a unitless way of calculating this. And this one is also dependent on the shape of the object, so the size doesn't really matter that much. So it's just whether it's a rectangle or if it's a circle or if it's something more complex than that. And we are also looking at the cross-sectional area, which is normal to the flow direction. So for an example, if we are calculating an ROV, let me try to do this it's a bit blocky, but it's still more or less 3D here. So we have an ROV with its manipulators up front. And when this one is moving forwards, so I'll just do so when the ROV is moving forwards and the waters are relatively calm, we won't look at any currents or anything here, then the cross-sectional area, which is normal to the flow direction, that's going to be the entire front here. So it's going to be the area marked with red. But then, if, for an example, this manipulator gets moved, they are often hinged fairly close to the edge here, and it's moved off, held to the side here at an angle, then you suddenly have to add the cross-sectional area there also that's sticking out of the main front of the ROV there. So that's going to be added to the rest of the cross-sectional area. So basically, it's whatever area that's hitting straight on the flow of the water. And in order to calculate the force of these drag effects, we use this formula. So basically, we do 1/2, and we do the density of the liquid. We put in the drag coefficient itself, and then we put in the cross-sectional area, normal to the direction of the flow, and then we put in the square of the velocity of the flow. So by having all of these, the drag coefficient we usually get from a table. So we look at the basic shape of the ROV, and we calculate in a table to figure out what kind of coefficient to put in there. And the density we will of course know already because it's seawater. And the cross-sectional area is fairly easy to calculate also. And the velocity is easy. If the thrusters are giving it a forward velocity of 3 meters per second or something, then that's what's going to be your velocity. So it's a fairly easy calculation to do. The main problem is often just figuring out what the drag coefficient is going to be. But we're going to look at that when we get a bit further on. So they've done quite a lot of experiments trying to figure out what kinds of values they're going to get with different kinds of objects, and then just basically using straight off geometrical objects, just like you have in your team projects in mechanical design. So cylinders, plates, cubes, spheres, stuff like that. And they've done many tests with them in pools where they are running flows of water across them, and they are measuring the forces that they are getting from it, and then calculating the coefficients from those forces, because then they will basically know more or less everything, all of the values, and then it's easy to go back and calculate the coefficients. So if we start up top, the first one is a sphere, where the radius is given with a capital R. And the way they calculate the added mass for it is they do 1/2 multiplied with the density of the fluid. And then it's basically just the calculation for a complete sphere in volume. And that usually means that we have a added mass coefficient, which is half of the drag coefficient, and the added mass coefficient is 0.5. So if you want to figure out the drag coefficient, you just solve this equation and then you get it. So the drag coefficient will be 1 in this case. Then we have a circular plate, and then we have a motion that is normal to the plate. So if our plate looks like this, our motion is going in these directions. So we're getting the full cross-section of the entire plate as the area. And again, we're using the basics of a sphere in order to calculate it. But instead of getting 0.5 there, we are putting in 0.6. And I'm guessing that has to do with sharp edges or something like that. As I told, these are measured values, so this is what they have calculated while doing tests on it. And they've done at least hundreds of tests, if not thousands, on each of them to verify that the values are correct. So these are sort of the averages of the values that they've tested to. And here it's a bit difficult to get I'm guessing at least it was a bit difficult to calculate a added mass coefficient, so they've just put in a drag coefficient, 1.8 to 2. So then you suddenly have quite a lot of extra being put in for the force from the drag there. So for a cylinder, where we have motion normal to the cylinder axis, so that will be similar to the one we set up in the previous lecture. Where we have the motion going this way, and the axis of the cylinder going through there. There is one thing that they're putting in here, and it needs to be quite a lot longer than the thickness. Usually when you use this much greater than symbol, we're thinking at least 10 times larger. So if you have a diameter of 1 meter, then you want at least 10 meters length on your cylinder in order to feel sure that you can use these values. And again, here we have put up the density, and this is basically just the volume of the entire pipeline. So you're putting half a cylinder up top, half a cylinder below. Just to do a quick calculations, you use the entire full cylinder of water for it. And you get the coefficient for added mass equals to 1 in this case, and 1 to 1.2 for drag. So you get slightly more on the drag side, but nothing near what you get on the circular plate, where you are up towards 2 in the coefficient. Yeah. Yeah, but basically, in this case, we are putting the axis of the cylinder in the same plane as we are putting the plate in. So that's why they get the same motion. But if the cylinder in this case was being lowered in a vertical position, so it's being lowered this way down, we couldn't use those values there, because then the motion would be parallel to the axis of the cylinder. So it has to be at a 90-degree angle compared to the axis of the cylinder. And then we have the next one, which is just a basic rectangle. Again, the one side has to be larger than the other one in order to look at this one. To be fair, the very first value they have here, they are saying that B and A are equals to each other, so I'm not quite sure why they are saying that B has to be larger than A. For some reason they're putting this in. But basically what we get here is a calculation for the volume of the added mass, and dependent on the ratio between the width and the length of the rectangle, you will get a value for K here, which is a dimensionless value, and you're putting that value into this calculation. So the basic, not the exact size of the plate. It doesn't really matter if B is 20 meters and A is 20 meters. It's still going to give you 0.58, just as B equals to 1 meter and A equals to 1 meter is going to give you 0.58, but it's the ratio between them, the size difference between them that counts here. So then we have several other ways. So if B is 1.5 times greater than A, you get 0.70, 2 times, 2.5 times, and 5 times greater. And then you see this K value increases with the larger this ratio is. But it is slowing down, as you can see here. So the increase is slowing down. The larger the difference becomes, then the less of an increase we get on this K value. And then for a cube where all of the sides have the same length, then we can put in this very simplified formula. And our coefficient for added mass will be 0.7 that of the coefficient for drag. So we will get the coefficient for drag will be equals to 1 divided by 0.7, which will be a number greater than 1. So we will get something larger there. I can't do that division in my head. So this is the basics also in the last part of the recommended practice from DNV. Yeah. Yeah, it's not all of them, as you can see here. Not all of them have all of the coefficients. So exactly why that is the case, I really don't know why it hasn't been put in here. If we look at the recommended practice from DNV, I think that one is a bit more complete, so it has more values to look at. It also has more cases to look at than this, so it has more different cases to look at, basically. But the main table is more or less the same layout in the DNV one, where you have basic shapes on this side, you have added mass, and then you have coefficients basically on the other side. So it's the same way of working inside the recommended practice. Only if I remember correctly, I haven't looked at it for a couple of years now, but if I remember correctly, it's a bit more complete inside the recommended practice when you're looking at it. So one thing we need to remember is to add water that is trapped inside the object. So for an example, in a pipe like this, it will of course be filled with water. As soon as you submerge it, it will fill up. But also if you have for an example a larger structure made up of many pipe segments, for an example a protective structure that's going to be lowered down over a subsea production system. It is usually made up of many pipes that are welded together into a cohesive structure, giving enough protection for the entire area. And those are usually hollowed out in some ways, so that they aren't welded completely shut. So they are made so that water can enter, and also if you are raising them up again, water can exit. So that's why they have holes in each ends of these pipes. Which means that as soon as you start submerging it, it's going to start filling up with water. But it might not fill up completely with water until you've gotten down to 50 meters, 60 meters maybe, because it will have pockets of air trapped in there, and the openings aren't all that big. It's usually something like this. That's the opening, which means that it will take some time to fill up with water, just get the correct flow going there, and air has to escape and everything. So. But then when we are doing our calculations, we would usually calculate that they have been completely filled with water, so that we will add this water mass to our added mass. The problem is, of course, for that first part, when you're lowering it down and it's starting to fill up with water, then you can get your center of gravity in your structure can be shifted, because maybe one side of the structure is filling up quicker than the other side, so the other side has more air trapped inside it, and then you would basically get it shifting a bit, and then you might get it out of equilibrium, so that air that is trapped inside on the one side, it won't escape at all, because it's being trapped in areas where it has no openings to exit the pipes. So you have to be very careful when you're doing these lowerings into the water. Make sure that everything gets fully filled with water. I know that on some structures they actually do create lids, sort of rubber lids, which they put into place in these openings where it's supposed to be able to flow in water. And then before they actually start lifting it from the deck, they actually pre-fill the entire structure with water. And then once they put it down into place, an ROV goes over and it just removes all of the lids, so that you will have free flow of water coming through the structure. Because that's a good way of making sure that you won't have any of this center of gravity trouble when you're lowering it down. And one thing we need to mention is that all of the table values that we looked at and everything that's in the recommended practice from DNV, all of those are for steady flow. So nothing of it is for turbulent flows. So that was the aim of my bachelor thesis, was to be able to figure out a way to use the software to calculate coefficients when we had a turbulent flow instead of a steady flow. We never got that far. We got so far that we managed to verify the steady flow values in the tables. So we managed to recreate those in the software, and we started looking at doing turbulent stuff, and also putting in heave motions where we were slowly oscillating the flow, basically. So if you are lowering, for example, if we're lowering this plate down, and you also have heave motions as you are lowering, then you will have on the wire coming down from the crane, you will have a certain velocity. And that one will be constant. So V1 will be constant, for an example, 0.3 meters per second, slow lowering of it. But then you will have the waves coming into the ship, so the waves will be lifting the ship and it will be lowering the ship. So you will have, if we do a velocity for the waves, wave motion, the heave motion, then this one can be, it can, for an example, go from negative 0.5 meters per second to positive 0.5 meters per second, which means that every now and then, when the wave is sort of at the bottom or at the top, then you are going to be moving at exactly V1 downwards, but the flow is going to be different. As soon as the wave is starting to move downwards or upwards, you're going to have to put the relevant velocity for the waves, and you have to calculate it into the velocity of the object, because the whole system is starting to move. And of course, when we are calculating for the flow velocity. We're not calculating for the object velocity. The object velocity will be V1, because that's where you're lowering it down. But you also have to look at the flow that's moving and everything. So it becomes really complex once you start looking at it. So we started putting that in, and we saw that this was probably a task more suited for a master's degree and not a bachelor's degree. So we never got that far. We got to really test out this stuff. But it was really interesting to look at. And experiments on the drag coefficient for oscillating flows, which is basically what I was talking about here, where you get the heave motion in. So oscillation just means that you're moving in a sinus curve in it. And it is greatly increased compared to the flow you get when you have a laminar flow going past it. And this is because, of course, even though you are lowering the object down, you will have, in this local area, the object will be moving like this. It will be gradually moving downwards, but it will be moving up and down in that area, where we get these vortex creations, and the object has to constantly pass back through an area where it has just created vortexes. So we get a lot of turbulent flow around the object. So we assume that we can at least double the coefficient when we're talking about an oscillating flow. But in the recommended practice, it also states that there have been experiments done which show that a doubling might not nearly be enough. So you might quickly look at 5 times, 7 times, maybe even 10 times as large of a coefficient when you have an oscillating flow like that. Depending, of course, upon each situation, but you can quickly see that having some way of calculating this in a computer program would be very beneficial for the companies that are doing this kind of stuff. So that I can really understand why they gave us that bachelor thesis, but they should have aimed for a master's thesis in my perspective. It was a bit too much for us. Basically because a bachelor thesis is approximately half a semester that you're working, while a master's thesis is often 2 semesters. So just getting the time to work on it would have been more beneficial for a master's thesis. And so we also have complex structures. Basically, most of what we do out there can be considered complex structures. An ROV will also be a complex structure because the ROV doesn't have steel plating all around or anything like that, so it's not a massive thing. It has quite a lot of openings where water can flow through, which means that you will get a lot of vortex creation and turbulent flows inside the ROV itself when the water is passing through it. It of course means that since much of the water has the ability to pass through parts of the ROV, you won't get as much of a cross-sectional area to put in for your added mass and everything. But still, that's basically the only way to simplify it, is to just look at it as one block instead of looking at it as it really is. And as mentioned, you use model experiments or computational fluid dynamics, as it's called, when you're doing it in programs. Model experiments is the typical of creating, for example, if you're going to test a rig with the heave motions and everything of a floating rig, then you would create a model of the rig that was to scale. So for example, 1 to 20 scale or 1 to 50 scale, depending on the size of the rig and the size of your test area. So they have one up in Trondheim in a center called Marine Tech, which is connected to NTNU, which is the sort of national university for technologies here in Norway. And they have a really, really advanced pool where they are testing stuff. So really big pool where they can have huge models in it, and they have wave generators that create waves and everything. So they do a lot of this, and I know that most of the business, oil and gas business, they want model experiments when they're going to do stuff like this. So they want to have videos and pictures of this model floating up and down in the waves in the pool that they have. And then all of the values that they get from this, they want to use those instead of going for the CFD option, where just the fact that for model experiments, especially if you're going to try to figure out, like the guys who figured out the new front for a ship, the Expo, if they were going to do absolutely every idea they had to improve this design and create a physical model and put it through rigorous testing in a pool like that, it would cost quite a lot of money and it would take a lot of time. If you instead can do most of your design reviews in a computer program, just doing simulations and seeing that, well, this design worked, this design didn't work, we're not going to continue with that one, we're going to continue with this one. And then you do some alterations to it. Well, that didn't work, we're going back to the original one, and then we're doing some other alterations. Well, those worked, we got some better values, we're going to continue with those. So you get this sort of iteration process where you do small changes, and for every small change you do, you can do a new analysis in your CFD program. Because once you've set it up, once you've got it properly set up, it is pretty easy to just exchange the 3D model for a new one and put it in there and run the test again. Which means that maybe the computer, the server where you're using, that's doing the analysis itself, maybe it has to use a day or two to run this. But while it's running it, the engineer can work on something else. So it's nice to do that. You can just put it off, have it running in the background, and then you're working on something else while it's working. And then once you get to the point where you see that this is really good, we have excellent results on our analysis, now we can create a model and we can put it through model experiments. And most likely you will be fine with just one model and one round of experiments just to verify that your simulations are correct, instead of building a whole range of models and doing several years of testing to try to get everything done. So it's a more efficient way of doing it, but the old way is still creating physical models and putting them through the tests. And when you have some experience in this, so when you've been working for a while, maybe you have experienced colleagues which you can tap into their knowledge and stuff like that, then it doesn't become easy, but it becomes possible to calculate the added mass and drag for complex structures. So because if you have been a part of, let us say, 50 lifting operations with fairly complex structures, where many of them were sort of similar in ways, then you will start seeing similarities between them. So you'll see that, well, when I have a structure that looks like this, I can expect this much. I can expect a coefficient that's around this area. And if I have a structure that looks slightly different, the coefficient is going to change just a little bit, and then you have the experience to do these sort of mental calculations where you don't actually calculating before you sit down and calculate them, but you're sort of thinking through what have you seen, what have you experienced, and how can you put that into your new calculations. But again, that comes with experience, so it's not something that anyone is expected to do once they're done at school. The alternate is to make use of the simplified methods that we've already started looking at in order to calculate it. So basically just simplifying the entire structures, looking at different ways of calculating just parts of the structure and then adding those together afterwards. So things you can do to simplify it is that if you have pipes or plates that are very close to each other, and they then will have larger values than what they would have individually, because the gaps will become, especially the closer they are, the smaller the gap will become, and the more restricted the flow through that gap will be. It will basically be throttled while it's going through the gap, which means that most of the flow will go on the outside, and that means that even though you have two pipes, when you're putting them close together, it will act as one pipe. So you will get a larger, basically more like a plate instead of a pipe. And if they are placed directly in front of each other, or behind, so that one is directly in front or behind, then you will have lower values, because one of them will basically be in the shadow of the other, so that it won't be as affected by the flow and the drag forces as the first one is. And of course, the one that is behind, it will most likely be inside the added mass of the one that's in front, so that you sort of get an even larger benefit from it. And if you have smaller parts that are placed in front of or even behind of larger parts, then they basically won't do anything. If it's placed in front of, it is most likely, if it's a really large part, it's most likely in the middle of the hydrodynamic mass, so it's not going to have any effect. The water around it isn't flowing, it's just staying there, so that that part won't have an effect. And if it's behind it, the same happens. It is also caught inside the water cushion there. And if you have plates with small openings, so for an example, if we're just looking at the circular plate, if it was a perforated plate, so that it has loads and loads of holes in it, going all the way around it and all over the surface, then you can do an approximation where you reduce the added mass proportionally to how much it's been perforated. So basically doing the perforation ratio will be looking at how much area have we lost through the holes. So basically all of the holes combined, how much area is that? And then look at the area that is left. So then look at the total area, because then you will get a ratio between them. How much has been hollowed out and how much is still there. And you can use that and look at it in proportion to the added mass. But even though you can lower the added mass in that case, your drag will usually be greater, because you will have a lot more turbulence. Because all of the water flowing through the holes, it's going to create a lot of vortexes on the other side of the plate, so that it will create quite a lot of drag there. I think we'll do a break before we go to the next slide. thought I hit the wrong button. So in case you haven't seen it on Time Edit yet, I've made some changes to our Thursdays, so that the Thursdays when we're having usually have subsea technology in 2085, where I have to dig out the webcam and everything, get poor quality recordings. I've managed to switch those around a bit. So this Thursday we're going to be in this room, and it's going to be a bit switched between Auditorium F and Auditorium D, I think. So it's a bit back and forth though, so just keep an eye on Time Edit which one it is, but I've managed to switch all of those subsea lectures on Thursdays that we still have left to rooms where we have proper recording capabilities. So yeah, we were looking at complex structures, and we're going to get to see a couple of clips from the first one of them is from actually the Marine Tech one up in Trondheim, and they're testing. It's a ship called Sea Orbiter, where they're doing model tests on it, and it's a really weird ship because most of the ship is submerged. So you can see all of this huge plate here with the diver that's supposed to be underwater, and then there's just a little part up top here that's supposed to be sticking up. So it's some sort of experimental ship they're doing with here. But this was just more to show how it works when they're doing model tests. And this is 1/15th scale, so it's 15 times smaller than what it would be in real life, the ship. So they're first just positioning it, so they have a diver helping them, putting it in place. Because of course, if they're going to get any values from this, they need to have some wires connected to it with force sensors. And here you can see the wave generator. This is a massive hydraulics going on there, pushing on the water, creating waves. It's basically the same as you can get in these recreational pools, where you get the wave generator. It's basically the same system that's being used. We're also using massive fans to create wind, so that you get that effect also. So this would be equivalent to more than 10 meters of height on the waves. And here we're looking at the waves coming from the side, 10-meter waves. So that's how it's supposed to look. So there's the surface of the water, so you have all of this underneath water, and the rest is above it. So it's a really funky-looking ship, but I think I haven't really looked at what they're supposed to be using it for, but I think it's for research purposes. So basically, having all of this area underneath, there's supposed to be a lot of window ports where they can look at marine life and stuff like that. So I don't think it's a cruise ship. Let's see. Then we can look at the other one. They're also doing model tests, but this time on a semi-submersible rig. And here you can see it's actually connected to pistons that are measuring the force that's coming. And they also have pistons. The pistons are the ones that are doing the motions here, so they don't have external waves breaking over it. So this would be a smaller tank that they're doing it in. So then they have to move the vessel itself, or the model of the vessel. But by reading off the values on these pistons, they can get the resistance from it, so that they get pretty accurate values. But the only thing they get there is the heave motion, so just straight up and down motion. So they are not getting anything more than that. So we also have a couple of examples of how to do calculations with this stuff. So we're going to basically just look at the example calculations that are in the book and go a bit more through them. So the first example is that we have a quadratic plate, a construction that looks like a quadratic plate, and it's being installed in the horizontal position. So we basically have a plate. And it has equal length on all sides here. So we can just call that the length A. So it's completely quadratic, and it's being installed. I'll just do it on the side here. So we have length A, and it's basically being moved up and down. So in this case, I think it's low. It's being installed, so it's being lowered down in this case. And the dimensions we have, so our A measurement here, that's 10 meters, so it's 10 by 10 meters in size. And it weighs 10 tons, this plate, when it's on the deck of the ship. And it has a volume of 5 cubic meters. So it's going to displace 5 cubic meters of water, which is equivalent to 5,000 liters. So it's quite a lot of water it's going to displace, so it's going to feel some buoyant force. So once we have managed to fully submerge the entire plate, we can look at what weight we're going to get then. So we will get the mass of the plate, which was 10 tons, and we subtract the density of the fluid with the volume of the fluid displaced. We multiply it with G, so we get this. The density of seawater is 1.025. So if you remember with the density of water in general, it's 1.0. So regular tap water is 1.0. But seawater has so many minerals and salts in it that it weighs a bit more. So we calculate it as 1.025. And actually, it's the same with the density of seawater as it is with gravity. It changes where you are in the world. So it changes a little bit, but that 1.025, it is sort of the average around the world. So you won't be far off if you use it. So then we get a weight of 47.8 kilonewtons for this one. So that's going to be the exact weight. And we can see that once it's submerged, a full 10 tons multiplied with 9.81 is going to give us almost 100 kilonewtons. So we can see that we are below half the weight of the plate once it's fully submerged in water. So then we're going to look at the hydrodynamic mass in the vertical direction. So when we're moving it up and down, how much mass are we going to get on these cushions above it and below the plate? So then we have this calculation. So this is an excerpt from the table that we looked at earlier, where we are using a rectangle, but we are also saying that B is equal to A, so that we get the 1 value here. B divided by A equals 1. So we can use K equals 0.58. And then we just insert what we have. We know the density of the water. It's 1.025. K is 0.58. Of course, we know what pi is. and our A measure and our B measure, they're going to be the exact same. So we get 10 to the square of 10 there and multiplied with 10 again, as we get it here. Put in all of the values, and we get 467 tons. So here we can see that we have a 10-ton plate, and we have 460 tons, or almost 470 tons of water being moved along with the plate. So that just shows how incredibly much larger the added mass can be. So our total mass, when we are looking at it, is, of course, we have to add in the 10 tons of the plate itself, so we almost get 480 tons as a total mass here when we're moving it. Which means that if we're going to pull it back up again, we have to really think about the crane that we're using. We can't use a 20-ton crane, because a 20-ton crane can handle all of that hydrodynamic mass. So we're going to have to use a 500-ton crane instead in order to be able to actually lift the stuff. So lowering it down is going to be fair enough. You don't necessarily have to have a 500-ton crane, but considering that you're going to almost 99% be sure that you're going to have waves, so you're going to get this heave motion while you're lowering it down, which means that every time the waves go up, you're going to be stretching your wire with approximately this weight. So you really do want this crane to be able to handle everything. And of course, you wouldn't have most likely you wouldn't have a 500-ton crane. In this case, you would have one that was even more, because you would be on the safe side. Especially as we talked about with oscillations, where you can easily get twice as high of a coefficient on it when you're looking at it, and then getting quite a lot of oscillations, you would quickly end up with a lot more than 500 tons there. So for plate constructions, hydrodynamic mass can greatly exceed the dry mass, as we've seen here. We can get huge numbers for the hydrodynamic mass. So now we're going to look at a steel pipe, and now in the horizontal position, as we've looked at a couple of times before already. So we have the steel pipe, and it's being lowered down this way. So we have these movements going on. So we have an outer diameter of half a meter on the pipe. So it's a pretty large pipe. You get it approximately there, that diameter on it. And we have a wall thickness of 25 millimeters, so 2.5 centimeter thick walls. And it's 10 meters long in this case. And the density of steel, we assume it to be 7.8. It is usually around it. It depends a bit. Is it austenitic steel? Is it stainless steel? It varies just slightly. But if you round it off to 7.8, it's usually around there it's going to be. If you want to be on the safe side, round it upwards to 8, so that you do 8 tons per cubic meters. Then you're definitely going to be on the safe side for it. And of course, we have the seawater there, as we've looked at before. So first off, we don't know the weight of the steel pipe, so we're going to have to calculate the volume of the pipe itself. And in order to calculate the volume of the pipe, where we set up, I don't know why the example is using the radius when it's giving the diameter out there, but that's basically what they're doing here. They're just giving the radius of 25 centimeters, and they're subtracting the wall thickness basically here. So it's figuring out what's the radius inside, the internal radius of the pipe. So we have the diameter of 0.5 meters. That was unnecessary. which means that we have a radius going to the outside of 0.25 meters. And since we have a wall thickness, which is 0.025 meters, we're going to have a radius here on the inside. And R will be equal to 0.25 minus 0.025. So that's basically what's being done here. It's just calculating. It's just doing the full radius minus the internal radius in order to get the volume. And 10 meters of length, so it gets the volume of the steel itself in the pipe. Which means when we multiply it with the density of the steel, then we get the mass of the steel. So it's almost 3 tons of steel in this one pipe. Which means that in air it's going to weigh 28.5 kilonewtons. So when they're lifting it off the deck, they have that much force pulling on the wires. And when they are submerging it, so we get those 28.5 kilonewtons, and we subtract the density of the water, the acceleration of gravity, and then the volume of the steel itself. So we get it down to 24.8 kilonewtons. So not that much buoyancy on this one compared to the plate where we were more than halving the weight of the plate itself by lowering it in. While here it's much more dense. So most likely the plate that we were looking at in the last example, it was either not made out of steel completely, or it was made out of, or it had pockets of air inside it, or something like that. So for some reason it didn't weigh. It wasn't solid steel like this pipe is. So when we start looking at hydrodynamic mass in the vertical direction for this one, then we need to think about the half cylinder up top and the half cylinder below. So then we look at our table again. So we look at cylinder. We have a length which is far greater than the diameter. It's 20 times greater than the diameter, so it's not a problem using this one in this case. And then we can put in the density, which we already know, the density of the water. And we have the diameter squared and the length of it. That's going to give us the combined 2 halves of the cylinder of added mass. And that gives us 2 tons. So the steel itself of the pipe was almost 3 tons, and we have almost 2 tons of added mass from water. But then we also have to remember that the pipe is hollow, so we have water inside the pipe also, so we have to add that. And then we're using the internal radius to calculate the volume of it, because then we're only looking at the inside area here, where it's filled up with water. So that gives us well over 1.5 ton, that one also. Which means that our total added mass is 3.6 tons approximately. And then we add in the weight of the pipe also, so we end up at 6.5 tons for just that one pipe. So something that weighed around 3 tons when it was lying on the deck of the ship, it's going to end up being twice that, and then some, when you get it into the water and start moving it. So if we assume the same pipe as we just looked at, so we're keeping all of the values that we just had, all of the volumes that we've calculated. Then we look at the submerged weight of it instead. So we get 8.8 kilonewtons, because now we are I have to look at this one just to see what happened there. Oh yeah, that's right. So basically what's happened now is that we have shut off the ends of the, and there was some text that should have been in there. We have shut off the ends of the pipe, so now it's filled with air. It's not filled with water anymore. And this means that we now have, instead of removing just the volume of the steel, it's no longer just the volume of the steel that's displacing water, it's the volume of the entire pipe itself, because there is no water inside it. Which means that we get a much more buoyant pipe. So we go from the 24.5 kilonewtons to 8.8. So we are getting a much lighter submerged pipe in this case. And of course, when we now calculate the hydrodynamic mass, there is no water inside it, so we don't need to add that one. We only get the cylinder above and below. So then we just get roughly 5 tons on this one. So this just shows that whether something is filled with water or whether it is filled with air, it's going to have some effect on the weight. But of course, if you're filling it with air and you're lowering it down to 500 meters, 1,000 meters, 3,000 meters, you need to have the strength in place in the steel, or else the steel is just going to collapse. So if you have too thin walls on the pipe, it's going to basically just be compressed like a soda can if you fill it up with air. So it's not ideal having something filled with air when you're putting it down. If you are filling it with air, it should be there for a purpose, like having loads of electronics equipment inside it or something like that. Then it's okay to have it filled with air, but then you've also designed the walls to withstand the pressure that you're placing it at. So then we're going to look at a suction anchor, which now means that we have a vertical cylinder instead of a horizontal cylinder. You remember the images we saw of suction anchors? These huge, almost looks like silos that they are going to place down on the ocean floor. So they're really big, but they're also usually closed off at the top. So if we look at a cross-section of the suction pipe, if you're going to lower it straight down, you're going to trap a lot of air inside here. So you're going to need, you do have some valves up top here, because you're of course going to suck vacuum in there to make it suck itself into the ocean floor. But the problem is, if you're lowering it down straight like this, to begin with, you're going to fill it up completely with air. So you're just going to start compressing the air until you get to a point where it might actually tip over and release all of the air out. Just the same as if you take a regular glass and you put it upside down into water and you start pushing it down, then you will, if you're just pushing at the glass, then after a while it's most likely going to flip to one of the sides. As soon as it gets some sideways force, it's going to flip to the side and release all of the air. So you can actually end up getting the same effect on something like this. So you need to utilize the fact that you have these valves up top. They have to be open so that the air can be allowed to escape from the top, and you have to be very careful when you're lowering it down. So don't lower it down too fast, because you only get a certain amount of airflow through the valves. So if you're lowering it too fast, then you are going to submerge it completely while you still have quite a lot of air left inside it. So you want to do it at a very slow pace. Make sure that all of the air gets a chance to escape before you fully submerge it. And in this case, we are assuming, just for simplification, that the holes up top here that allow the air to escape to begin with, we're not going to let those affect our calculation. So we're calculating as if it's closed when we're doing the calculation, which is going to give us a more conservative calculation, of course, because we are not allowing flow through it. So we have an outer diameter of 5 meters. So it's pretty huge, and we have a height of 8 meters. And we have a mass of 35 tons, so these weigh quite a lot. So if we do the calculations to get the volume of the steel, so we can start off with the mass and divide it with the density of steel, so that we can get the volume. So we get approximately 4.5 cubic meters of steel volume. And we already know the mass, so it's very easy to calculate the weight in air. And we, of course, need this volume in order to be able to calculate the submerged weight once we've managed to fill it up completely with water and then lowering it down. So you can see we have roughly 45 kilonewtons in buoyancy here. So the weight isn't much affected by the buoyancy compared to the total weight. So then we're going to start looking at the hydrodynamic mass. So in the vertical one here. So let's see what we're doing. We're looking at the vertical direction of movement. We are getting two contributions. So we are getting the circular plate up top here. So this one will act as a circular plate, and we can look at it there, because we have the same diameter down here as we have up here. So whether or not this plate is at the top or whether it is at this end, we are still going to get the same half sphere of added mass on both sides. Because the water that is inside, it's going to be trapped in here anyway. So that water is just stuck there. It's not going to be replaced by new water as we are moving it downwards. Of course, if we had this opening here, we would have some flow going through it. So then we would have a completely different scenario for calculations. But that would have then we're moving into complex structures again. So we want to stay at the simple structures for this course. So we need to calculate both the cushion on the top and the bottom, and also the water that is trapped inside the suction anchor. So we look at the table, and we see that for a circular plate, we get the radius r of the plate, and we just punch it in. We know the density, and this is a straightforward calculation when we're looking at hydrodynamic mass here. So we put this in here, and we get 42.9 tons. And that's just the weight of the two cushions. So we haven't looked at the internal trapped water yet. So when we start looking at the trapped water, we can set up this calculation for it. We basically do the calculation for a water volume equal to the entire outside of the suction anchor. But since we know the volume of steel itself, then we can just subtract that one, and we will get the volume we have in here. Instead of starting to try to figure out what's the internal radius and what's the length up here and everything like that, we can just do the entire thing and subtract the steel, since we already know the volume of steel. So when we put these two together, we get quite a lot of added mass on this one. And most of it, as we can see, is just the mass of water that's trapped inside the anchor. So if we're looking at the horizontal direction, so if for some reason we needed to move it this way, or that we actually wanted to lower it down. I'm going outside the camera bounds here, but we want to flip it over on the side as we were lowering it, so we're going to look at that possibility. So instead of lowering it down like this, we will lower it down on the side instead, and we'll see what kind of values we'll get from that. Because now we can look at, if we just look at the cross section this way, we basically get a rectangle that is covering the entire cylinder. So we can simplify it as looking at a rectangle, because we only have 8 meters of length and we have 5 meters of diameter. So for the cylinder one, we needed a length that was greater, fairly greater than the diameter. So it needed to be at least 10 times as great. So we can't use the cylinder one in this case, but we can look at it as just a rectangle instead when we're just looking at the cross-sectional area. So that's going to give us a slightly higher value than if it was a cylinder, but still we are going to be able to calculate it. Yes? Yeah, the trapped water will still be a problem, but we're going to see if we can somehow get a smaller value for these cushions at the top and bottom. So we're just going to compare the possibilities of lowering something in a different position and then tilting it to the correct position when we get it down to the ocean floor. So then we look at this one, and if we do 8 divided by 5, we end up fairly close to 1.5, so that we get 0.7 as our K value in this case. So we're going to put in the K value of 0.7. And since it's we get this added mass for the short cylinder, so 112 tons. So it's a bit more actually than if we look at the straight up and down one. And the trapped water is of course the exact same. So because the volume hasn't changed inside the suction chamber, the only difference is that now it's on its side. It's not vertical, which means that we get 270 tons in this case. So this was not a good idea to flip it over. It ended up becoming heavier when we flipped it over. So would be the best idea is to put it down like this. But if we had done the same for the first example, the plate, if we had lowered the plate in a vertical position instead, then we would practically have no hydrodynamic mass in it, no added mass at all, basically, because it would just be the thickness of the plate and the width of it. So instead of having 10 by 10 meters, we would have 10 meters and then just the thickness of the plate. So it would be quite a different calculation there. Yeah, that was the last one. So for a suction anchor, we don't really get much effect. Basically, we get negative effects of flipping it over. But for the plate, we can gain quite a lot with putting it over on the side. And that is what is done on quite a lot of different structures that are lowered subsea, is that they actually flip them into a vertical position when they are lowering them down. But then, of course, you get the whole operation of managing to flip it controlled back into a horizontal position before you reach the bottom. Usually they stop like 20, 30 meters above the seafloor, and then they flip it back by the help of ROVs and different equipment they have. Maybe they have some additional cranes that are helping. So, for an example, in the instance of the plate, so if we have one vessel that is lowering the plate here, that was a really big plate compared to the vessel, but and then you have an assisting vessel also that is that is connected with slack lines to the other side, to the bottom of the plate, basically. So that when you're lowering it down with this one, all of the weight is on this crane, so you're lowering it straight down, but you're not getting all of this added mass that you would get if you were flipping the plate already. So you can lower it almost all the way down, and then when you're almost to the bottom, this one starts pulling upwards, and then you can sort of get it level on a horizontal plane. And then you only get your added mass for the last couple of meters, or 10 or 50 meters before getting it into place. So it's a much more controlled situation when you're doing your lift. So that's one of the ways that they flip these, that they actually have several vessels that are working together. Or if it's a large enough vessel, it has multiple cranes, so it can actually do it with just the cranes it has on board and manage to get it done that way. But it depends a bit on the size of the vessel, of course. So I think instead of starting on the next appendix, I think we're just going to leave off for today. So we'll be going back to part 3 next week, no, on Thursday, and then we'll be looking at Appendix A